Have you ever heard of the IMO? It's the pinnacle of high school math competitions. Every year, 100 countries send 6 of their nation's brightest minds to come together and tackle some of the world's hardest math problems. The 6-question test is split over 2 days, with 3 problems given 4.5 hours on each day. At first glance, these problems can look impossible. However, the beauty of the IMO lies in how often a single flash of insight or a unique perspective can turn these seemingly impossible problems into something surprisingly manageable. Today we'll be looking at one of these questions, a problem proposed for the 1997 IMO that has an especially elegant solution. Rather than giving the solution straight away, I would like to guide you through how someone like you could have stumbled upon this answer on their own. Here's the question. Let A, B, C, D be a regular tetrahedron, essentially a triangular pyramid that has equal side lengths, and M, N distinct points in the planes ABC and ADC respectively. Show that the segments MN, BN, and MD can be the sides of a triangle. How do we prove the existence of a triangle? Where do we even start? For starters, as with many math problems, it's usually a good idea to simplify the question into a simpler case in order to get a better feel for the problem. Here, the tetrahedron maps to a triangle, and the planes map to lines. So now the question becomes, an equilateral triangle ABC with M and N being distinct points on the lines AB and AC. Prove that the segments MN, BN, and CM are the sides of the triangle. Now the question is much easier to understand, but it's still hard to solve. How do you prove that a triangle can be formed? Imagine we're handed 3 line segments. If one of them is much longer than the other 2, there would be no way for those 2 shorter segments to connect back to the long one. And if the sum of the shorter 2 segments exactly equal the length of the longest line, well, all you really get is a straight line. This means that a triangle would only form if the sum of any 2 side lengths is greater than the third. Great, we now have a rule for checking if 3 lengths can form a triangle. But here's the real challenge. How do we find those lengths in the first place? There's all sorts of natural steps we can take here. Maybe we plot the graph on a coordinate plane, or maybe we use some sort of trigonomic approach. And while those are all perfectly valid approaches, let's try to find something simpler. Rather than proving a triangle exists by checking if the side lengths can form a triangle, what if we instead see if it's possible to construct a triangle ourselves using these side lengths? By definition, a triangle is just a shape formed by connecting any 3 points that don't all lie on the same line. So, if we can find 3 such points where the distances between them match the given side lengths, say MN, BN, and CM, we can prove that a triangle exists. We know that points B and C are both fixed and that points M and N can move around. Therefore, to limit the amount of uncertainty in our new triangle, we should choose M and N as 2 points of our new triangle. But where should the third point go, so that no matter where points M and N end up, the triangle has the correct side length? Let's start by matching just 2 of the side lengths, MN and BN. We already know that the side MN is shared by both triangles, so we've already matched that side. To match BN, we extend a perpendicular line from point B past AC so that AC cuts this line in half. Let's call the endpoint of this line D. Now if we connect M, N, and D, we've got a triangle that matches BN and MN. But what about the third side, CM? Let's do the same thing for CM. Extend another perpendicular from point C past AC so that the perpendicular line is split in half. And we can call this endpoint E. We now have 2 points, D and E, each forming triangles with 2 of the desired side lengths. But here's the catch. We need 1 triangle, not 2. How do we combine D and E? Here is where the critical insight lies. What if, instead of looking at the question from a 2D perspective, we step into 3D? Imagine rotating the line BD around AC. This rotation generates a whole range of possible D points, all of which maintain the required side length. Do the same thing for CE. Now, wherever these 2 rotations intersect is our golden point. We can call this magical point F. Connecting M, N, and F gives us a triangle where all 3 side lengths, MN, CM, and BN, match perfectly, and the problem is solved. In fact, if you visualize it, this setup creates a tetrahedron ABCF. Wait a second. The sides of ABCF look awfully similar in length. Are they? Going back to when we drew the perpendicular lines, if we connect AE, it's clear that AE shares the same lengths as the sides of equilateral triangle ABC, as they are hypotenuses of right triangles with the same side lengths. The same can be said for EC, DB, and DA. Now, what if instead of rotating just the line, let's rotate the triangles ADC and AEB? We can clearly see that the lengths of the tetrahedron are all the same. You can also think of it this way. Imagine balancing the regular tetrahedron ABCF on the edge AC. No matter where N is on AC, the line segment NF to NB is the same. The same can be said for line segments MF and MC. Let's take a moment to recap. From our original problem, we descended to a simpler 2-dimensional case, where we figured out that we can construct a triangle with our desired side lengths by choosing a point in the 3rd dimension. Now, can we extend this to our original problem? Instead of going from 2D into 3D, can we now go from 3D into 4D? Surely not. What is the 4-dimensional equivalent of a tetrahedron? Well, when you go from an equilateral triangle to a regular tetrahedron, or a tetrahedron with equal side lengths, you get a shape with 4 points, where all of the combination of 3 points form an equilateral triangle. Similarly, the 4D equivalent is a shape with 5 points, where any combination of 4 points form a regular tetrahedron. Let's label the vertices A, B, C, D, and E. Don't worry if you're having trouble understanding this shape, as human brains are not made to think outside of 3D. How about, instead of visualizing this shape in 4D, imagine that it is a solid object, and that we are looking at it from a perspective where we can only see 3 dimensions, or the tetrahedron A, B, C, D. We're trying to prove that the lengths MN, BN, and MD can form a triangle. All we really need to do is accept that there exists a point in the 4th dimension. Let's label this point E, where EM is the same length as DM, and EN is the same length as BN. This 4D point E is defined exactly the same way as how we defined the 3D point earlier. If we connect M, N, and E, we've proven such a triangle exists and its sides match our desired lengths. Easy, right? We started in the 3rd dimension, moved down to 2 dimensions only to go back up to the 3rd dimension and all the way up into the 4th. So whether it's a 2D triangle, a 3D tetrahedron, or even a 4D hypershape, the power of creativity and a bit of clever geometry can solve problems that seem completely out of reach.